Okay, so today we're going to start a new unit and we're going to look at forces. So here's our note page for forces. And you will notice vector is up there again. This is now the third time we have talked about vectors. We talked about it in the very first unit, in the first quarter of this course. We also talked about vectors in our previous unit that we just took an assessment on when we did motion and motion maps. So here we're looking at a vector again. So at this point, it is my expectation that you know what a vector is because this is the third time it is showing up. A vector is a quantity that requires a direction in order to fully describe it, and it is represented by arrows. We've looked at vectors in our first unit of the year. We looked at it last unit in terms of velocity and acceleration, and in this unit we're going to look at vectors in terms of force. The size of the arrow tells you the magnitude. The direction tells you the last unit, the movement, for example. Okay, so in this unit is going to tell you the direction of the force. So a force is defined as a push or a pull on another, or that the body exerts on one another. Okay, it is going to give energy to the object. So basically, we've spent a lot of time this year talking about energy in terms of chemical reactions, talking about energy in terms of velocity and acceleration, and now we're going to look at energy in terms of forces. All right, so energy is the driving factor behind a lot of things in the world and how it works. Energy can make our object start moving. It can make our object stop moving, and it can change the direction in which the object is moving. So some examples here would be the acceleration of a car. All right, so a car accelerating, maybe it's at a red light and the light turns green, so the driver pushes down on the gas pedal and the car begins to accelerate. The force that the floor exerts on your feet. Now, this is kind of funky sounding because when you stand on the floor, you don't actually feel a force being exerted back up onto your feet, but the reality is it's there. You're pushing down on the floor and the floor is pushing back up on you, and we're going to really dive in and look at this in more detail. All right, it's called the normal force, and we're going to look at that a little bit later on. So a force can be exerted on the same direction, so it can be in the same direction, or it can be in an opposite direction. And we have two main forces. We have an unbalanced force and we have a balanced force. So an unbalanced force is when the overall force of an object is exerted in one direction. So the net force, which we're going to define down here, is in one direction. A balanced force is when we have equal forces which act in opposite directions, and therefore there is no motion. So the difference between an unbalanced and a balanced force is an unbalanced force is going to give motion. For example, if I take my pencil and I push it, that is an unbalanced force. There is a force in the upward direction causing my pencil to move. Now, if I push back on my pencil with the same force I push up, guess what? Notice the pencil is not moving. That is a balanced force. So there's a force in two directions, but it is the same, so no movement. All right, I mentioned a net force a minute ago, so let's go ahead and define what that is. A net force on an object will change the velocity of an object, its direction, or both. So again, going back to my pencil, The net force, if I move my pencil upward, is in that upward direction. Now I can change the velocity, the speed. Notice it moved a lot quicker. Or I can even change the direction. All right, so I can move my pencil in a different direction. So we have a net force causing movement. Let's look at forces, an example in terms of a tug of war. All right, so if we are playing a tug of war and both teams are pulling in the same force, but opposite directions, and we can tell that through our vector. This vector means motion or force, force is being pulled to the right. This vector shows there's a force being pulled to the left, but because the arrow length is the same, the magnitude of that force is the same, therefore there is no movement. But let's say I increase the magnitude of force to the right. So I have a larger force moving right than I do moving left. In this case, I would have a net movement to the right. So let's look at friction. Friction is an opposing force caused by the contact of two surfaces. And friction is going to cause a moving object to slow down and finally come to a stop. So if you think about it, if you're riding your bicycle, you're pedaling. If you stop pedaling, what happens to your bicycle? It slows down and it eventually stops. Why is that? That is because of the friction between the tires and the road, all right, causing that bicycle to stop. Now, friction does depend on a number of different things. It depends on the mass of the object. It depends on the gravitational force, all right, that would be gravity. It depends on the type of contact surface. So some surfaces have more friction than others. And it also depends on the type of friction produced. So we're going to look at the different types of friction, and we're going to really dive into this in much more detail. How does mass affect it and things of this nature as we move through this unit. Let's take a piece of paper, pull the paper out, and what happens to the object. All right, so if I was to take a piece of paper and I was to quickly pull the paper out, well, it's kind of hard on this. I don't really have a good example here. Let me zoom out a bit. If we pull it out, the pencil stays for the most part in the same location if I pull it out quick enough. Why? Because I've pulled out my paper fast enough to overcome the force of friction. But what if I pull it out slowly? So if I pull it out slowly, what happened to my pencil? My pencil went with the paper because I did not pull it out quick enough to overcome that force of friction. So let's look at Newton's first law. And this is the law of inertia. This is defined as objects in motion tend to stay in motion at a constant velocity. And remember, velocity is speed of an object with the direction, unless a net force acts on the object. So things that are moving will stay moving. The object at rest tends to stay at rest unless a net force acts on the object. All right, and that is true because if I take my pencil and I set it down, it's going to remain right where it is until what? I apply a force to it and move that object. So Newton's first law is called the law of inertia. So inertia is the tendency of an object to resist change in motion. All right, so we're resisting change in motion. So this is going to go back down to forces. The larger the force, the more likely we are able to make something move. For example, if we were to go outside and our car is in park, and if you were to push on the car, chances are the car is going to stay right where it is located, right? You're not pushing on that car with enough force in order to get it to move. And if you've ever broken down on the side of the road and had to push a car, you know it takes a couple of people to get that car pushed and really get it going. All right, let's look at gravity. Gravity is the force an object exerts on another object. So the gravitational force between objects depends on, again, mass and the distance between objects. So our gravitational force increases if mass increases, or if distance between the objects decreases. So the closer two objects are together, the more gravitational force there is between those two objects. So if I have two beakers here, there's a gravitational force between these two beakers. Now, if I move these beakers further apart, this distance has increased. The gravitational force between them has decreased. So let's look at this. Place a beaker on a table with a piece of paper on top and some beans. Now, I'm going to place another beaker on top. And it tells me to pull out the paper. So when I pull out the paper, oh, I should have chosen a different beaker. My beans are not, hold on, there we go. So it tells me to pull out the piece of paper. So here we go. What happens when I pull out the piece of paper? What's happening to my beans? My beans all fell into the bottom of this beaker. Why? Because of gravity. Gravity is exerting a force on the beans, and so the beans will fall down into the beaker. Weight is different from mass. And up to this point in science classes, you may have heard these defined kind of as the same and used interchangeably, but the reality is mass is how many particles are in a substance. Weight is the measure of the gravitational force on an object. So it is the relationship between the mass of the object and the force that is being exerted on the object from gravity. All right, we are going to measure this in newtons, which we use a capital N for, and the acceleration due to gravity is 9.8 meters per second squared. You can also sometimes see meters per second squared written as meters per second per second. So that is two ways in which you may see that unit appear. Now, you don't need to memorize this. Of course, you probably at the end of this unit will have this memorized because we're going to use it so much. But if you check out your reference tables, you'll see here the acceleration due to gravity is 9.8 meters per second squared.